to go. So yeah, I was thinking maybe start with something a bit different, like disconnected from what we saw yesterday, but that might be useful for the coursework. So for the coursework, a lot of the circuits you have to implement are actually, if you think about it, just a bunch of wires. So it's probably a good idea to just use a big like mix box and then try to find a way to describe how the wires are moving from the inputs to the outputs. And then when you're proving that they're correct, for instance, you could split on the inputs and or do a proof by induction or something. But it's probably a good idea also to just do some equational reasoning so that you're taking existing facts that have already been proven for you, and they would typically be imported at the top of the module to give you a hint of what might be useful, and then you can just combine them. And so here's a fairly artificial definition to try to see how one would go through this process. So here the key word here is postulate. So I'm just assuming that these things exist, and I'm not giving a definition for them. So this really forces me to use the facts that I've provided in the block, because I cannot rely on the implementation of length to actually prove its properties. So I've postulated a function length that, given a list, will give me its length, a natural number. And then I've postulated the fact that length is an instance of fold_r. So fold_r, if you remember from the Haskell course, will take a function and a base case, and it will apply the function to all of the values in the list in a sort of telescopic manner, and then ending up with the base case. So essentially, if you want a visual representation of it, fold_r replaces the empty list at the end with the default case, and then all of the cons constructors with the function you passed it. So here I'm postulating that fold_r of successor, so it's adding 1 to whatever the current value is, with a base case of m on x's is equal to m plus the length of x's. So it's really saying that there are length x's constructors in the list x's, which makes sense because length is the thing that's counting the conses in a list. And then I have, right, so fold_r here is also postulated. I cannot do any proof by induction or whatever. But I have this fact about fold_r. So if I'm computing the fold_r of x's append y's, if you think of the way we are doing this, so we have the default value at the ends, and then for each value, we're going to combine it using C instead of cons with the tail. So when we have this, it's equivalent to first computing the result of fold_r on the list at the end, because we're doing so the base case, then C with the last element of y's on the base case, then C with the one before the last element of y's on top of that intermediate result, and so on and so forth, all the way until we reach the middle, the append. And so this first fold_r is basically the intermediate results that will have been computed when we are at this middle point. And then we'll just keep doing fold_r more on top of that result. So that lemma, you can prove it if you want. It's just a true statement about fold_r. And then what we want to prove is that length implemented, well, we don't know how it's implemented, but we know it's equal to this specific fold_r, actually distributes over append. So the length of x's append y's is equal to the length of x's plus the length of y's. So in the coursework, you will have a lot of properties like this, where you have a map on the outside and append on the inside, or you have some map and concat. You have various functions that you want to push through each other. And this is how you would do it. So I think originally I wanted to do the nasty version first, but let's just do the proper version immediately. So what we do is that we open the equational reasoning module, and it's giving us, so this is a good thing to get used to, it's giving us these combinators that allow us to write a derivation. So here we have three combinators. So we have begin to say, I'm going to start my proof. Then you have proof steps. So it's saying from here, I can move to here using this justification. And then you have the QED symbol saying, I'm done now. It's a valid proof of the statement. And so the way I set things up typically when I want to prove something like this is to just throw in a lot of intermediate steps. Then you get a bunch of yellow. It doesn't matter. It's just telling you that for now, it doesn't know what the intermediate values are. And that makes a lot of sense because when you're doing a transitivity step, there's a bit of, this is where you need to be creative, right? Because you need to come up with that intermediate step. But we are here, so I can just solve my goals. So I know that I'm starting from the left-hand side, and I want to end up on the right-hand side. Okay? So then one of the crucial steps, well, so for now, I'm not going to write down the derivation. I'm just going to write down what I would like the proof to be. And to get a sense of what I would like the proof to be, the only reasonable thing to do, if you're not looking at the implementations because you're trying to reason at a higher level than actually trying to run the functions, is to look at the properties that you have for these functions. So here, I want to talk about length. The only thing that I know about length is that if I have m plus length of something, then I get to unfold it as a value. And what do I know about plus? Well, I know that 0 is a neutral element for plus, right? So my first step is going to go to this thing so that I've transformed my original goal into something that is amenable to using this reasoning step, right? So then, assuming that I'm using this reasoning step, I should be able to go to foldr lambda soc 0 x's y's, right? Because the length, I'm calling it on this expression. This is the one that shows up at the end of the foldr, so it seems like a reasonable thing to do. And then what do I want to do? Well, I have this property about foldrs and append. So I'm just going to assume that it's going to work. So what if I copy paste a bunch of stuff? So it's a folder of a folder on top of like some values, whatever. Okay. And then, okay, so then I'm sort of stuck here. Like I don't really know what the next step is. So maybe we can start from the conclusion instead and try to make some progress from the conclusion. So that's one of the advantages of looking at these as derivations with both a start and a finish is that you can actually go in both directions, right? Or even if you have an idea of where the two directions should meet in the middle, you can already put in your statement in the middle and sort of try to derive the various steps that are going to get you to where you want to be. If you're just using transitivity, you sort of always are looking at the goal left to right, which is a hindrance, in my opinion. Okay, so here I have length x's plus length y's. And the only thing that I can use is, again, the result about length. So I may want to apply it, and then I would get something like, so a fold R, of lambda soc length x's on top of y's. Okay. And now the thing that I have here sort of looks like this through that lens again of the unfolding. So I can say I should get folder lambda soc folder lambda soc z. Okay, maybe I'll introduce another step again. So this length x's looks a lot like 0 plus length x's. And then that's an instance of this thing. And now they should actually, they should meet in the middle, and that should be fine. So I think it makes more sense to sort of try to find your proof this way, because you can focus on actually finding the path from one end to from the start to the beginning before worrying about the exact proofs that you need. Otherwise, you might spend a lot of time trying to put the proofs together, but you're actually going down the wrong path and you're not going to be able to connect back to the goal. So what's the point of like trying to come up with these proofs? So here we're trying to come up with something that sort of makes sense, hopefully, and then we can justify the various steps. Okay. So let's start with the first one. Okay. Oh, what? I accidentally killed Emacs. All right. Let's start with the first one. Oh, right. Okay. So the goal here, I mean, this is what I was saying earlier, right? 0 is neutral for plus on the left, but this is actually true just by computation. So here I can just remove the need for a justification, and we have this other combinator allowing us to just transform things into one another when they just happen to be true by computation. But this leaves a trace in the document, right? So you're remembering the sort of path you took along the proof. So then the second goal is saying that length of x is, well, okay, the 0 has disappeared now, so it's a bit annoying. But it's basically a call to this function. So I can just use it. It even manages to find the arguments. I don't like that 0. I'll put the 0 instead. Okay. And now we need to prove that if you have a folder over an append, then it's the nested calls to folder. But maybe some of you will have spotted that there's some kind of issue here. It's gonna work? No, it doesn't work. So maybe we can, okay, that's, look at the goals. And okay, so my hopes were that C and N, I don't know, but X's and Y's were supposed to be this. And if you look at what we have and what we want, the problem now, well, first of all, it's in the wrong direction, so I can use symmetry. Okay, now it's in the right direction. I have a folder of X's append Y's, with like some function in some base case, except that here we have the y's on the outside and we have the x's on the, no, we have the x's on the outside here, and here it's on the insides. So when I wrote my derivation, I made a mistake. It's in the wrong order, but that's fine because I didn't try to put in this proof, so it's not invalidating all of my work. I can just try to fix up this mistake, push through the changes, so the x's becomes y, and the y's becomes x's, and here I have lengthwise. Hopefully these steps are still valid, and then I'm not quite at the conclusion that I wanted, so I can add an extra step. Oh. If I can type. Yeah, that should, okay. Okay. So back to the proof that we wanted. Now they should be lining up. So x's append y's, x's append y's, y's inside, x is inside, x is outside, x is outside. So I can fit this in, solve for the function in the base case. Then I have this intermediate value here. So here the idea was that this thing inside looks a lot like 0 plus length of, okay. It looks a lot like a call to length as folder. So here we need to go slowly. So, oh, actually, this is what we saw the other day, right? We want to act on a specific sub-expression. So the easiest way to do that is to copy-paste the goal that we have. And because it's documented in the code here, it's really easy to grab. And then say, OK, the whole I want to act on is this sub-expression. OK. And so now we are left with our instance of length as folder. 0 y's. So if it doesn't type check, I just compare the two. And again, it's just backwards, so I can just use symmetry to fix up the error. Now this is another step where we're going from 0 plus something to that thing. So it's a free step. We can turn it into one of these coercions. And then we have another instance of that function, length as folder. Again, with these things and x's. Oh, it's taking only 2 arguments. It's again backwards, so we can take the symmetric of it, blah, blah, blah. Is it able? Yeah, it's able to find the right default case. And then we have this off by 1 thing, which is the result of the fact that I was interverting x's and y's. But because plus is commutative, we should be able to conclude this question. Is it not in scope? Maybe I need to import it. So if you need any, I don't think you should need any extra results for the coursework. But if you've gotten a solution which is different, which is not the same as the one that I have, you may need extra properties. You can just import whatever you want. Actually, I might show you something. So here, I don't know how it works in VS Code, but here I've imported all of the properties of the natural numbers. And I know that I want something that involves plus and commutativity. So I can do Control-C, Control-Z for search, of course. And then I can say that I'm looking for plus. And because I know the conventions of the standard library, okay, that's maybe a bit harder to do. I know that com is probably going to show up in the name of the result. So I'm saying I want this identifier to show up in the type, and I want this substring to appear in the name of the lemma. And it's giving me a bunch of stuff. So there's the one that I want, saying that plus is commutative. Of course, we're using various definitions. There's a weirder one here, but that we are not going to use. Can I think I should be able to, yeah, there we go. So if I use Control-U before the search operation, just like for all the other commands that we have, it will actually normalize the goal. So you can see that here the algebraic definitions, whatever, commutative has been reduced to just the facts that we want. So even if you don't know the name of the thing, you can find it. Okay, if you don't know that it's going to be called something com, you can just use for plus and equality, and you'll get much more results, but it's still way fewer than if you go dig down into the data-net properties file yourself. So I've got this thing, and oh shoot, is it? No, it's the other way around. Length x's and length. There we go. Right, so hopefully that's useful. If you need to prove some results in the coursework, it's tempting to always perform induction, but sometimes you can just reuse a bunch of things that we've already proven for you, and it's hopefully easier to go down that road rather than having a proof that's 10 times as long, because you're basically re-implementing a version of the proofs that are already in the standard library. Okay. Now, going back to what we were looking at yesterday. So yesterday we were looking at decidability and sort of search procedures. And we proved, among other things, that equality on the natural numbers is decidable. Then we defined what it means to be odd or even. And we proved that we could actually decide whether we're one or the other. Then we saw this search function, the Markov's principle, which is not provably terminating in ACTA, but we feel like is a good reasoning principle. So sometimes we can reach for things that are just beyond what ACTA offers us, just as long as there's a computational meaning associated to these principles. And then the thing I wanted to look at, so we saw this proof system for what it means to be even. And if you remember, we're saying that, well, you're either 0 or you're the successor of an odd number. And if you're odd, it's because you're the successor of an even number. And so it's a total proof system. We can always prove that all of the even numbers actually are even, but it might be a bit noisy. So here I have an example. I want to prove that that 100 is even, and I can do that by proof search. Agda is still sort of happy to do it, so I can zoom out maybe a little bit. Yeah, that's the proof. But it's really boring, right? It's just 100 sucks and then a 0 at the end. Okay. So let's try to see if we can do better than that. So if only we had a function that, given a natural number, would give us a proof that it is even. That would be super convenient, because then we could just say is even 100, and we would be done. Of course, it's not quite provable, because not all of the even numbers are actually even. So the trick here is to use the search procedure that we saw the other day, yesterday, to get ACTA to generate the proof for us. So we're saying, well, the machine knows how to decide whether something is even or not. And I think Connor's tagline is, why keep a dork, and bark yourself? Why keep a dog and bark yourself? Why keep a computer? Why have a decision procedure on hand and write the proofs yourself? So the idea here is to find a way to express that the decision procedure is going to tell you, yes, it is indeed even. So let's see, maybe I can write it like, let's do it like this. So rather than focusing just on being even, we can actually express that statement for arbitrary computations. So what does it mean for a decision procedure to say, yes, you indeed have a proof of A rather than not A? Well, very easy. We can inspect the decision, and if it's yes, we're saying, well, it is true. We don't have it in scope, okay? So if the decision procedure is telling us yes, then we know that the statement is true, it holds. And if it's telling us no, then we say that it's just impossible. It is not the case that is yes holds because the decision said no in the first place. And so then here we can say, well, if only I knew that the natural number you gave me is even. Oh, there was a question mark. So if I ask the question, is n even, and the procedure tells me yes, then I'm happy to give you proof that n is even. And the implementation here will be trivial because basically the work is being done by this even decision procedure. And then the is yes constraint is ensuring that we only need to consider the case where it succeeds. So let's see. I probably want to introduce that constraints here explicitly. So here it's the usual question when we want to prove something. What can we match on? Well, we could match on n, but morally, even is already doing that work for us, right? Even is the thing that takes n apart, looks at it, is it even, is it not? Why should we be doing the same work again? We don't want to do that. We cannot split on the constraint either because is yes is a definition by pattern matching, and it's stuck because its argument, even on of n, is not either yes or no. It's just a stuck computation. So what we do here is that we use the with construct, and this is where we get to see that it's actually magic. So the with construct, if you remember, it just extends the current definition with an extra pattern corresponding to the result of this intermediate computation. But it's not doing just that. If you look at the type now, zooming in even more, you can see that the type of the constraint is not mentioning even question mark n anymore. Now it's mentioning p, which is this intermediate result obtained by calling even question mark n. So we are not just collecting the results, we're also recording in the type that this value now corresponds to that pattern. And so now when we make observations by inspecting the pattern, the type itself will get more and more precise. And so now P has type deck of something, so I can just pattern match on it. And of course, it's keeping one of the cases, but let's write it anyways. So in the positive case, maybe zoom out a little bit. The intermediate computation returned this proof that n is even. And because we said, okay, it needs to say yes, and it did say yes, the constraint collapses to something trivial. And so we can return that proof. And in the no case, Agda didn't even list it originally because it's obviously impossible. Why is that so? Because the intermediate computation reduced to no, and so is yes of no reduced to the empty type, And we saw that the empty type is impossible. So now this can just be discarded. So I could match on constraints, or I could just leave it out entirely. So really what we're saying is that now we can use this function at compile time on concrete values, and the even question mark program will run on that value, and provided that it is actually even, will actually give us a proof. But we don't need to write sucks, etc. We just get the program to generate it for us. Of course, it doesn't always work if you try to prove that even 101. Here it will complain. So it's a bit of a strange complaint. Okay, maybe I could do something better. Ooh. Let's be fancy. So instead of using the empty type, I can declare my own empty type that said, okay, so this is a fancy empty type that says this. So here, if the decision procedure returned yes, I'm still happy, so I'm not saying anything. And if it returns no, I just return the empty type that says this is a no answer. And so if we look at the error here now, it's telling me that the proof that it computed, which is just as horrible as the one you would have needed to write by hand if you were proving even 100, is a proof that 101 cannot be even. Okay, that's maybe a bit noisy, so let's go back to bottom here. So this is a very general principle that's called proof by reflection. The idea is that you're running a computation at the type level to do a proof for you. And because enough things are concrete, the computation actually manages to go all the way through and give you an answer so that you don't have to write the proof by hand. Of course, you need to write the decision procedure. Not all problems are decidable, so it can help you for problems that are easy to prove but annoying to prove. Okay, I guess we can prove something even better. So how does it go? It goes something like this. If I have a deck A, is yes, D, A. So instead of having to re-implement this pattern for every single predicate that I want to decide, I can implement it once and for all. Or is it, that might be a keyword. I can say, okay, I want a magic proof of A. So it's exactly this stuff. D constraint with the, oh, I can actually match on it this time. Actually, I don't need to do the width. Oof. I don't even need to talk about this. Proof P. And now I can replace this stuff by just saying magic even 100. So this is the essence of this proof principle. If you know that you can decide a problem, then you can actually get proofs for free on concrete values by running the decision procedure and observing that it's indeed returning a positive answer. All right. And then the other thing I wanted to do is, okay, so we've seen when we're doing the proof search, we've seen various quantifiers. So this is a spoiler, I guess. Oop. Full. Not this one. So we saw that if you have a domain that you can enumerate, you can search it, but it will not get accepted by ACTA. However, there are weaker notion of existence and universal for all that are actually finite. And so you can actually search through them in a principled manner and in a manner that's terminating, that's seen as terminating. And these are the finite quantifiers. So let's look at these ones. So I'll start with all. So all takes a predicate and it lifts it. So this is a predicate on values, and it's going to construct, well, you can see it as a family on lists or as a predicate on lists. So it's going to lift that original predicate to all of the values in a list. And this is a very generic pattern. You can write the same thing for that will lift a predicate on values to all of the values stored in a tree, to all of the values stored in a graph, whatever you want, all of your existing data structures. And here we're abusing ACTA notations, and we're saying, okay, well, what does it mean to prove that P is true of all the values in the empty list? Well, it's trivially true, so we have a constructor for it. And then what does it mean for P to be true of all of the values in a list that starts with X? Oh. Oh. What does it mean for P to be true of all of the values in the list that starts with X and continues with X's? Well, P better be true of X, and then P better be true of all of the elements in X's too. And so again, this has exactly the same structure as the list, so we're using the same constructors. Okay. So then, for instance, we can collect proofs that, let's see, 0, 100, 20, 42, they're all even. And how do we go about this? Well, it has exactly the same structure, so ACTA should be able to figure it out. I didn't want it to do that. To figure this out, we will have as many conses as we have conses in the original list. I don't know why it's storing in a bunch of parens because they're not needed. I see. And then we can just say that all of these are indeed even numbers. Okay, but this is maybe not the most exciting of things. However, it's not limited to properties, right? If you remember what we were saying about predicates the other day, predicate is the term we use to talk about families over a single type, but they can actually be interesting data structures. They don't just have to be properties. So for instance, we can say that we have vectors of natural numbers for all of the numbers. This time I'm not going to use big ones. In the list 0, 1, 2. And so what does this correspond to? Well, it will be a triangular matrix, right? Because you have like 0 value here, then you have 1, then you have 2. So you can see that you have sort of a triangular shape. And you can then build it interactively. So that should be something like this. There are as many values as there are constants in the original one. And you can see now that the vectors we're expecting, their length are exactly matching the arguments that we have in the old constructor. So all should really be understood as a way to build interesting data structures that have complex indices rather than just like storing proofs that all of the elements in the list are even or whatever. It is possible to do it, but you can also have more interesting things in an all. Okay. Maybe I should put a bunch of vectors here. So the first one is empty, the second one has 1 value, and the third one has 2 values. All right. So that was for universal quantification. So this is saying all of the values in the list satisfy that predicate. But of course, you can also have existential quantification. So it's the same idea. You get a predicate and you get a list. And then you start to think, what does it mean for a value in the list to satisfy the predicate? So if the list is empty, there are no values in it. So there's no way for a value inside that list to satisfy the predicate. So we won't have a constructor for it. And then if the list is non-empty, well, you have a head and you have a tail. So there are 2 possibilities. Either the value you're looking for is at the head, or it's at the tail. And therefore, you have 2 constructors. So it could be that my value of interest is somewhere inside the tail. So it's not the current one, it's the next one. Or otherwise, with 1, if we can prove that P is true of X, then it's true of any value. Well, it's true that there is a value somewhere in X-axis that satisfies P. And now I think I will leave it for you to try to implement if you want to have a bit of fun. So now we can take the type that we had for, I guess it was a different one for, well, we had 2 types, to be fair. We had this one, and we had that one. So you can pick whichever you want. So now we should be able to actually implement this search function for these modified quantifiers in a way that is seen as terminating by acta, because we've reduced the search space from all of the natural numbers to just whatever values are stored inside of x's. So we should be able, by induction on x's, to go through all of the possible values and decide which one is the one that satisfies the predicate. And just like for the Markov case, it's because we have the strong assumption that it's not the case that that the negation of the predicate holds of all of the values, that we know that at some point we are supposed to get one. And I think, yeah, I'll stop here if you want to have a go at implementing it. It shouldn't be too hard.